Okay, this is video 9 in the grade 12 chapter Work, Energy and Power, and today we're eventually getting on to the concept of power. So to illustrate that, we're going to look at this example here. We've got two cars, same mass, car A and B, and they're being accelerated to the right from rest, and both cars reach a speed of 100 kilometers per hour. Car A reaches that speed, goes from 0 to 120 seconds, and car B goes from 0 to 100 in 10 seconds. And we're going to calculate how much work has been done by the car's engines. So we've got two different engines, both doing a certain amount of work, and to calculate the work done, we'd need to know what the change in mechanical energy of this object is. It's moving along the ground, so there's no change in potential energy, but there is certainly a change in speed, so we're going to have to calculate a change in kinetic energy to calculate the useful work done. So in both cases, the initial velocity of each car is 0, so it starts from rest, and they both reach 100 kilometers per hour, so we need to convert that to meters per second. So 100 kilometers per hour divided by 3.6 is going to give us 27.78 meters per second. So both cars reach that final speed, but in different times. So I want you to pause the video and calculate the work done, the useful work done by each car. Since you've tried that, you would realize that the useful work done on the engine on each car would be equal to a change in mechanical energy of that object. We're converting some chemical potential energy of the petrol into useful energy, mechanical energy. And we said earlier that the car is not increasing in height, or its height is not changing, and therefore any change in mechanical energy would have to be a change in kinetic energy. So we know that a change in any quantity is a final value minus an initial value, and basically it comes down to the change in the kinetic energy. It's equal to the final value, because the initial value is 0. So the final value of the kinetic energy of each car is half of the mass, and here we said the mass of the car was 1000 kgs, and it reaches a speed of 27.78 meters squared. We have to square that speed, and if we put all of that into the calculator, we should get a value of 3.86 times 10 to the 5 joules. So that's how much useful work was done. Useful work is often considered to be whatever the change in mechanical energy of an object is. So if something's speeding up, then its kinetic energy is changing. If something's being lifted off the ground, then its potential energy is changing. So the useful work done by the engine is considered to be equal to a change in the mechanical energy of the car. So now let's consider something different. Let's calculate the rate at which work is done by each engine. We know that each engine is doing the same amount of work because the car is reaching the same final velocity. So I want you to pause the video and calculate the rate at which each engine is doing work. Alright, since you've tried that, a rate would be the rate at which work is done would be the useful work done per unit time divided by the time. And both engines did the same amount of work. But car A, the work was done in 20 seconds. So that gives us an answer of 19,300. And then we need to consider what our unit would be here. Well, we've got the joule per second. So the engine in car A is doing 19,300 joules every second. Joules per second. And car B, the useful work done divided by the time would be equal to the same amount of work being done but this time in a much shorter period of time, half the time, in 10 seconds, and we should get double the answer. We should get 38,600 joules per second. So if we compare these two engines here, they're doing the same amount of work, but car B is doing it in less time. So the rate at which it does work is a larger value, 38,600 joules per second. And what we've really calculated here is the power of each engine. So let's go to the definition of power. And the definition is on page 44 of your notes. So let's go there. And there it is on page 44. We've got power is defined as the rate at which work is done. There's the formula. Work divided by time. And we need to consider that power is made up of two scalar quantities, work and time. Therefore power is a scalar quantity, and it is defined as the rate at which work is done. So if we go back to the page, we've got the definition of power, the rate at which work is done, but that could be stated differently. We could define power as the rate at which energy is transferred, because we know when work is done, then energy, an equal amount of energy is transferred to or from an object. So power is work divided by time, or the rate at which work is done, and is also referred to as the rate at which energy is transferred. So when we're dealing with problems, we're going to be seeing that there's going to be some kind of change in mechanical energy. So a motor might be lifting an object and its potential energy is changing, or the car engine might be doing work on the car and changing its speed and therefore its kinetic energy, and these are changes in mechanical energy, and we're going to divide by time and we're going to get the rate at which work is done, and that's the power. So let's look at a unit for power. We said it was the joule per second, which can be written as the joule per second, and that we call the watt. So a power of 100 watts means that 100 joules of work is done every second. 100 joules of work per second. So let's look at a problem where we're not moving horizontally but rather moving an object vertically. We've got this 10 kg load that's being lifted through a vertical height of 5 meters, and that's done in 12 seconds. We're going to assume that this load is lifted at constant velocity, so there's no change in kinetic energy. So whatever work is being done by this motor would be a change in potential energy. So pause the video and calculate the power output of this motor that's lifting this load. Okay, since you've tried that, let's go over the answer. We're trying to calculate the power output of this motor. And power is defined as the rate at which work is done. But this time we're considering useful work. Useful work done is considered to be a change in mechanical energy. And we're going to divide that by time. The rate at which mechanical energy changes would be the power output of this motor. So we notice that there's a change in potential energy because the load is being lifted, and that potential energy would be simply be equal to the mass times the acceleration due to gravity times the height it reached. And we should be dividing by time here to get power. Okay, so the mass is 10 kgs, the acceleration due to gravity is 9.8, and the vertical height that this load was lifted through was 5 meters. And that was all done in 12 seconds. So how much work was done? Well, if we go to the calculator, we've got 490 joules of work done in 12 seconds. And that's going to give us a power output of 40.83 watts. So this motor is doing 40.83 joules of work per second.